A generic approach to the exploration of quantum dynamics using time-dependent perturbation theory. Time-dependent perturbation theory, which we have already introduced in the earlier module 6. In module 6 we have introduced it, and we are going to use the final form. But before we use that, we will just remind the basic features so that we can understand why and what are the context based on which this perturbation theory was developed, and how we are going to use that. So what assumption we make here in this entire problem is that this is a generic approach. I'll just show anytime when we use this time dependent perturbation theory, this is the approach we should follow. We'll assume that first we assume that the quantum system in absence of perturbation. So there is a perturbation. In this case, this is constant interaction potential. So this H dash is the perturbation, weak perturbation. But assume that in absence of perturbation, this is an important point to understand first, because this will enable you quickly employ time dependent perturbation theory if you have this idea very clear. So first you assume that in absence of the perturbation, that interaction process, in absence of the perturbation, the system is in a stationary let's say n state of the unperturbed Hamiltonian. So before the interaction process, I will assume that my system is in n state, particular discrete state, and this discrete state, how do I get that discrete state? In fact, I can get all the states which are available by all these states which are available, in other words the spectrum of the system from the Hamiltonian, unperturbed Hamiltonian, using the time independent Schrodinger equation. So all possible states can be explored using time independent Schrodinger equation, which is H naught psi k naught equals E k naught psi k naught. So k is, let's say k is starting from 0, 1, 2 like this way, and one of the states is actually n state, discrete n state. So one can get these states from the unperturbed Hamiltonian where perturbation has not been introduced and yet, and we can get that. So this one is the eigenstate of the system, and this is the eigen energy, the energy of the eigenstate, corresponding eigenstate. So this is something which is before t less than 0, which means it is I haven't started the perturbation, I haven't introduced the interaction yet. So all possible states can be obtained from this unperturbed Hamiltonian. Then the process of interaction, the process of interaction between two states is turned on at t equals 0. And what are the two states? The two states which are available. Here I have some states which are available. So n state, let's say I'll erase all the states. I do not need all these states. This is just for information. Now I have all states can be obtained directly from time independent Schrodinger equation, but let's say I have n state and then there are other states also. I will call it, let's say, m state. And here my intention is that all the states can be obtained from time independent Schrodinger equation, but interaction between these states, how these two states are getting coupled, interacting, they have to be coupled, then only they can transfer the population. So that coupling interaction process will start at t equals 0 time, and a weak perturbation, which is represented by this, starts acting on the system until t equals t1. So within this interval, 0 to t1 interval, this interaction process will be acting. And during this time, this 0 to t1 time, the system is time evolving as a function of time because they are coupled now. So the time dependent Schrodinger equation during this time interval this 0 to t1, when the interaction process is going on, during this time interval, time independent Schrodinger equation during this interval, and this is the interval when the interaction process is on, during this time interval only, the time dependent Schrodinger equation will give me instantaneous wave function. Instantaneous wave function I h cut h naught plus h dash psi xt. So this psi xt is the instantaneous wave function. This is the instantaneous wave function at any instant of time during 0 to t1 time. So during this time when the interaction process is on, during that time only I need to find out the wave function. And how do I get the wave function? From this time dependent Schrodinger equation. And as we know that this particular wave function, time dependent Schrodinger wave function, can be expressed in terms of its available stationary states. So psi xt is expressed as summation of ckt e to the power minus I e naught k t by h hat psi k0 x. That's the way we do that. So instantaneous wave function is nothing but a superposition state, and superposition state, and we are taking the superposition of all available states, and this ck, there is a meaning of ck here. What is the meaning of ck? Ck is the contribution of each state. In the end, it will in for the population. So ckt whole square, absolute value, so the square of absolute value of ckt will give me the population in kth state. So this is the general idea of any time dependent perturbative approach, where we will first find out all the possible states available associated with unperturbed Hamiltonian, that's the spectrum of the system, and before the interaction. Then interaction process will be turned on at 0 time, and it will be kept on for a particular certain time. During this time interval, the wave function will be time evolving. And how can I get the wave function? Wave function can be obtained from this TDSE. This is the instantaneous wave function at the time when this interaction is going on. And this wave function is expressed as a linear combination of all stationary states, where this expansion coefficient is related to the population, final state population, I mean the population of a particular state. So using that, if we say that, okay, I had n initial discrete state and I had another state m, and interaction process started. So what we'll do is that transition from a discrete initial state n to a discrete final state m due to perturbation, which is the interaction acting from t equals 0 to t equals t1 time. Until t1 time it was acting, and question is what is the final state population. So population at the final state m at time t equals t1, just immediately after the interaction process is turned off. Is turned off. At that time, we'll check the population in the final state, and population is given by this the magnitude square. This is the result of time dependent Schrodinger first order time dependent perturbation theory, and where we have this omega mn is given by the energy difference by this. So this is something which we get directly from time dependent first order perturbation theory, or in other words, I will just simplify this one as e to the I by h cut 0 to t1 time e to the power. So the population depends, this population depends on entire history of time. That's why we have to integrate this time. Okay, so this is another point to be noted here. The population depends entire history of time of interaction. That's why we're integrating, and so this is represented as I omega mn t. Then this entire integration part will just write down as mn dt, where hmn dash is nothing but this spatial integration. This integration is over space. So this is the term which allows the interaction between psi n 0 and psi m 0, these two states. This is n state, this is m state. Interaction between these two states. So because we said that the we have only constant, as we have pointed out before, that this interaction occurs due to non-adiabatic coupling. So this H, the form of H dash is that it is a non-adiabatic coupling. So it is a constant, it doesn't depend on time. So because it doesn't depend on time, we can easily integrate this expression, and because H dash is a constant, it doesn't depend on time, so we will integrate it. We'll stop here, and we will continue this session in the next meeting.